You know, when you pick up like a bottle of milk at the grocery store or maybe a box of cold medicine at the pharmacy, you probably don't give a second thought to that little black barcode on the side.
Oh, definitely not. It's just background noise.
Right. Or the expiration date. We just assume it's simply a part of the packaging. But if you really stop to consider it, that tiny square of ink is actually the digital nervous system of physical commerce.
Yeah, that's a really good way to put it.
I mean, it is the code that makes almost every physical object you interact with trackable, safe, and legal. Which brings us to our deep dive today.
Exactly. And, we take it completely for granted. You just scan it at the self-checkout, you toss it in your bag, and you walk out.
Yeah.
But the technology required to put that specific ink on that specific package at the exact right moment is actively fighting billion-dollar global crises right behind the scenes.
It's wild. So today we're pulling from an industry ebook on HP's specialty printing systems, specifically focusing on thermal inkjet, or TIJ, technology. And there's also a brief mention of HP's leap into bioprinters for pharmaceutical samples that we'll get into later.
Which is fascinating stuff, by the way.
Oh, totally. Okay, let's unpack this. Honestly, going into this material, I thought I was just going to read about how factories print labels.
Right, like standard office printers, but bigger.
Exactly. But it turns out before a product can even legally sit on a shelf and, look pretty, it fundamentally has to be secure. The sheer scale of the hidden war on counterfeiting mentioned in these sources is it's staggering.
The numbers are deeply unsettling when you really look at them. To put the global counterfeiting crisis into perspective, the source points out that in 2017 alone, Interpol and Europol seized 26.4 million liters of counterfeit alcohol.
Wait, 26 million liters?
Yeah.
That's not just a couple of guys making moonshine in a garage.
No, not at all. That requires industrialized, coordinated, global manufacturing and distribution. And it doesn't stop at alcohol either. It heavily impacts global agriculture. Like 25% of products in the pesticides and seeds market are illegal.
Wait, really? A quarter of the market?
Yes. Just think about the implications of that. You have farmers spraying unknown, completely unregulated chemicals onto crops that eventually end up, on our dinner tables.
That is terrifying, honestly.
Right. And in the cosmetics industry, brands are pouring $140 million into anti-counterfeiting and track and trace solutions just to ensure the lotion you put on your skin isn't toxic.
Jeez.
But the most alarming sector, by far, is pharmaceuticals. According to the data, 1 in 3 pharmaceutical companies are currently not ready for the serialization required by the FDA's Drug Supply Chain Security Act.
Okay, serialization meaning like they aren't prepared to uniquely track every single individual bottle of pills they manufacture.
That is the core of the act, yeah. The FDA requires an unbroken, verifiable chain of custody for every single prescription drug, right from the factory floor all the way to the pharmacist's counter.
Makes sense.
If a batch of heart medication is compromised, they can't just, guess where it went. They need to know exactly which trucks it was on, which stores received it, so they can issue an immediate surgical recall without shutting down the entire national supply.
Right, because shutting everything down would be a disaster.
Exactly. And the only way to achieve that is by laying down a unique, indelible, high-resolution barcode on every single item.
Oh, I'm struggling to understand something here. If an international criminal syndicate has the resources to flawlessly counterfeit like a $5,000 luxury watch down to the microscopic engravings, why are they stumped by a little square of ink on a bottle of pills?
That's a really common question.
I mean, can't they just buy a high-end commercial printer, copy a real barcode, and slap it on a million fake bottles?
What's fascinating here is how the physical properties of the ink actually interact with the digital infrastructure. Let's look at the digital side first. Think of serialization like a biometric passport for that bottle of pills. If you photocopy someone's passport, it might look real to the naked eye. But the moment you try to use that copy passport at an airport scanner, the central database realizes that the exact same digital fingerprint is also simultaneously trying to board a flight in London.
Oh, and it flags it instantly.
Precisely. You can't just print the same fake barcode a million times.
So even if the counterfeiters print a perfect replica, the moment it gets scanned at a warehouse or a pharmacy, the master track and trace database throws a red flag because that unique serial number has already been scanned somewhere else.
Exactly. But, and this is key, this system only works if the physical anchor, meaning the ink itself, survives the journey.
Right.
If the ink smears in a humid shipping container or rubs off when boxes scrape against each other on a truck, that product becomes invisible to the digital nervous system. It's essentially lost.
Ah, I see.
And this is where the chemistry of HP's thermal inkjet, or TIJ, technology comes into play, specifically their use of GMP-compliant solvent inks.
Yeah, the source mentions GMP compliance heavily. That stands for good manufacturing practice, right?
Perfect.
I always assumed that just meant, like, a clean factory. Hairnets and stuff.
Well, in the context of industrial printing on food and drugs, GMP compliance is fundamentally about chemical safety. The source imagery shows this perfectly on a bag of crunchy kale with onion and garlic and a pharmaceutical bottle labeled 3EXP+.
Okay, I saw those pictures.
The packaging for those products is typically a material called BOPP film, biaxially oriented polypropylene. It's that flexible, glossy, almost slippery plastic film you see everywhere.
Yeah, it's incredibly slick. If you take a standard marker and try to write on a bag of kale, the ink just beads up and wipes right off.
Exactly. And that is the engineering challenge. To make ink stick to BOPP film, you have to manipulate surface tension.
Like how?
Think of a freshly waxed car. When it rains, the water forms tight little spheres because it can't grip the surface. Standard water-based ink does the exact same thing on that slippery plastic. To break that tension, industrial printers use aggressive solvent-based inks that essentially bite into the top layer of the plastic to create a permanent bond.
But wait, if you're using harsh chemical solvents to basically melt into the packaging of a kale salad, how do you prevent those chemicals from migrating all the way through the thin plastic and contaminating the actual food?
Yes, that exact balancing act is what GMP compliance certifies. The ink has to be engineered to be aggressive enough to bond instantly and permanently to the outside of the packaging, surviving global shipping routes, without a single microscopic molecule migrating through the substrate.
Wow.
It cannot alter the composition of the pills or the food inside. It is an incredibly precise chemical threshold.
Okay, so we have a highly engineered chemical that bonds safely to slippery plastic, and it connects to a massive global database to stop counterfeiting.
Right.
But factories are pushing out thousands of these products a minute. If it takes even like 5 seconds for this highly specialized ink to dry on a bottle of shampoo, your entire manufacturing line is going to back up.
It is the ultimate manufacturing bottleneck. Security is entirely useless if it bankrupts the factory by grinding production to a halt.
Exactly.
The technology has to be flawlessly secure, but it also has to be exceptionally fast and reliable. For a long time, the industry relied heavily on older legacy systems, primarily continuous inkjet, or CIJ, and thermal transfer overprinting.
Yeah, the source notes a massive industry shift away from CIJ, but it doesn't really explain how the old machines worked. Why was continuous inkjet such a headache for these factories?
Well, the clue is in the name continuous. A CIJ printer literally fires a continuous, non-stop fountain of ink from a nozzle.
Non-stop.
Yep. To actually form letters or barcodes, the machine uses complex magnetic fields to deflect individual drops of ink out of the mainstream and onto the paper as it flies by.
That sounds insane.
It gets worse. All the ink that doesn't get magnetically deflected has to be caught in the gutter system and cycled back into the machine.
Here's where it gets really interesting, because that sounds wildly complicated. I mean, trying to use CIJ sounds like trying to fill a fountain pen on a moving roller coaster. You have a constant spray of liquid, magnetic deflection, and a recycling gutter, all running at industrial speeds. I imagine ink gets absolutely everywhere.
Oh, it does. It requires heavy, constant maintenance, moving parts, messy fluids, and volatile solvents that evaporate out of the continuous stream and degrade the quality of the recycled ink.
Sounds like a nightmare for the factory floor.
If you stop the manufacturing line for even a few minutes, the whole thing can gunk up. The transition to HP's thermal inkjet system fundamentally changed the mechanical paradigm of how factories print.
So how does the thermal inkjet system actually get the ink onto the plastic if it's not this continuous magnetic spray?
It relies on thermodynamics, and the mechanics happen in microseconds. Inside an HP TIJ printhead, there are microscopic resistors located right behind the nozzles. When a barcode needs to be printed, the system sends an electrical pulse to a specific resistor. That resistor instantly heats up to hundreds of degrees.
Hundreds of degrees? Wouldn't that instantly boil the ink?
That is exactly the point. It boils the ink in a fraction of a microsecond, creating a tiny vapor bubble.
Oh, wow.
As that bubble rapidly expands, it acts like a microscopic piston, forcing a single precise droplet of ink out of the nozzle and onto the packaging.
And then what?
The moment the electrical pulse stops, the resistor cools, the bubble collapses, and the resulting vacuum pulls fresh ink into the firing chamber for the next drop. And this happens thousands of times a second.
That is incredible. So instead of a messy, continuous fountain of ink requiring magnets and gutters, you have a completely closed system that only fires a droplet when a microscopic vapor bubble forces it out.
Exactly. And because it is a closed system, it introduces a massive operational advantage called long decap time.
Dap time.
Yeah. In a factory, the conveyor belt doesn't run perfectly 24/7. Someone has to pause the line to fix a mechanical jam or change a master roll of plastic wrapping.
Yeah.
With older continuous systems, that pause meant the ink would dry out in the nozzles. When the line restarted, the operator would have to manually purge the printer, wasting time, wasting material, and slowing down production.
But with a long decap time, the ink cartridge can just sit idle on the line without a cap, like snapping a classic video game cartridge into a console. It's just ready to go.
Exactly. The vapor bubble mechanism allows the printer to sit paused on a line, exposed to the air, and the moment the conveyor belt starts moving again, it fires perfectly on the very first try. The hardware itself is basically a self-contained snap-in cartridge.
You don't need a degree in fluid dynamics or magnetic deflection to change it out when it's empty.
No, you don't. And our source material includes a highly telling quote about this exact benefit from Robert Levesque, Jr., a manufacturing supervisor at Hilco Vision.
Oh, yeah, you remember that part.
He specifically called out their transition to the HP bulk solvent system, noting that it saves them money, provides uninterrupted production, and crucially, allows his operators to concentrate on their actual core jobs.
Right, because they're hired to run a manufacturing line, not to act as full-time printer mechanics, babysitting a messy, continuous inkjet machine.
Exactly. And if we connect this to the bigger picture, when you remove the need for constant maintenance, you immediately speed up the entire global supply chain.
Yeah, the source gives a really stark example of this with the global pandemic. When the world suddenly needed N95 masks by the billions, Asian manufacturers had to ramp up new production lines literally overnight.
And they overwhelmingly chose HP TIJ technology for those new lines. When you are building a factory floor during a global emergency, you just don't have time to train operators on complex magnetic ink gutters.
Definitely not.
TIJ was easy to implement instantly, and because they utilized the GMP-compliant ink portfolios, it automatically met the rigorous safety standards for medical devices and pharmaceuticals.
And the numbers back up that efficiency across the board. The material notes that shifting to this specific technology results in 25.7% faster product life cycles and 10.5% more efficient warehousing.
It's massive.
You are literally getting physical goods into the hands of consumers faster because the microbubble ink dries quicker and the factory printers don't constantly break down.
Right, but to maintain that speed across millions of different products, the chemistry inside those snap-in cartridges has to be heavily tailored to the physical surface it's hitting.
Yeah.
You can't just use one universal vapor bubble ink for everything in the world.
I was wondering about that because as a consumer, a barcode on my glossy medicine blister pack looks functionally identical to the barcode printed on the brown cardboard box it shipped in. But mechanically, those surfaces couldn't be more different.
Night and day.
Yeah.
And that is why HP engineered distinct portfolios to solve very specific material challenges. Let's look at the three main pillars here. First, you have the HP TIJ 2.5 solvent portfolio. This is the heavy-duty chemistry we discussed earlier, designed specifically for those non-porous substrates. The untreated films, the foils, the slick plastics where normal ink would bead up like water on wax.
Okay, so that handles the pharmaceutical wrappers and the glossy food packaging. But what about that cardboard delivery box?
For porous materials, where the ink is meant to soak into the substrate rather than bite into the surface, they use the HP TIJ 2.5 aqueous portfolio.
Aqueous meaning water-based.
Right. Because it's absorbing into paper or cardboard, it doesn't need aggressive solvents. Instead, the engineering focus is on producing high optical density and incredibly dark, sharp black ink that achieves a resolution of 600 dots per inch.
Wait, why do you need a resolution that high for a simple cardboard box? I mean, nobody's admiring the artistic quality of a shipping label.
It's not for the human eye, it's for the digital nervous system. As barcodes evolve into complex 2D data matrices and QR codes containing massive amounts of serialization data, the physical squares that make up the code get microscopic.
Ah, gotcha.
If the edges of those microscopic squares bleed or look fuzzy on the cardboard, the automated warehouse scanners can't read them, and the package gets lost in the system. The 600 dpi aqueous ink ensures the code remains razor sharp even as it soaks into porous paper.
And then the source details a third portfolio, which honestly seems to be engineered purely for insane scale.
Yes, the HPTIJ 4.0 aqueous system. This is the powerhouse designed for extreme high-volume manufacturing. We talked about the microscopic vapor bubbles firing thousands of times a second, right?
Yeah.
Well, the 4.0 system scales that up to achieve printing speeds of up to 150 meters per minute.
Wait, 150 meters a minute? That's roughly 500 feet per minute. You're talking about a football field and a half of packaging flying past a print head every 60 seconds, and it is using microvapor explosions to hit a perfect 600 dpi barcode on every single item without blurring.
It's wild, isn't it? And it does it with a wider 22 millimeter printing swath, meaning it can lay down much larger 1D and 2D barcodes in a single pass without needing to slow down.
That's incredible.
It can be gravity-fed from massive bulk tanks or pressurized to keep up with the ink demand, and engineers can stitch multiple print heads together to print huge labels seamlessly. It is a completely different beast than a desktop printer.
Which actually makes the final section of our source material so fascinating, because we've spent this entire time talking about the macro-level global pharmaceutical supply chains, millions of liters of seized counterfeit alcohol, football fields of plastic packaging flying by at 500 feet a minute.
Right.
But the final step of any supply chain is you, the individual consumer. And here, the technology pivots away from cold utilitarian tracking into something deeply personal.
This raises an important question, really. It highlights a major shift in modern manufacturing. Brands are constantly trying to figure out how to balance the financial need for high-speed mass production with the modern consumer's absolute demand to feel individually recognized.
Yeah, because nobody wants to feel like just another barcode in a database. People want products that speak directly to them.
Consumers are actively rejecting mass-produced anonymity.
And the source material outlines a massive industry trend toward customization, short-run production, and what they call micro-markets. And the wild part is the exact same thermal inkjet technology that is coding massive industrial factory runs is also powering compact desktop printing.
It brings industrial-grade printing right into the brick-and-mortar store. The visual examples in the source material really highlight this shift toward hyper-personalization. We see boutique shopping bags heavily branded for a store called Stay Chic.
Oh, and those customized short-run labels for Celia's Sweet 16 Wildflower Honey.
Exactly. We see premium juice bottles specifically printed with the names Jane's Juice or Mike's Juice.
So what does this all mean? It's quite a paradox, because the underlying vapor bubble technology that applies an FDA-mandated, globally tracked, GMP-compliant security barcode to a bottle of heart medication to prevent an international crisis is the exact same underlying technology sitting on a desk in a local shop printing a vibrant, beautiful, warm label for a teenager's birthday honey.
It really is.
The elasticity of this technology to scale from global security to a Sweet 16 party favor is just amazing.
But even when it scales down to the desktop, it never loses that core DNA of absolute precision and security. The same reliability that prints Jane's Juice is being heavily utilized for highly secure in-house applications.
Really? Like what?
We are talking about government agencies utilizing desktop HPTIJ printers to print secure passports, localized ID cards, and classified government documents. They get the high-resolution, counterfeit-proof reliability of an industrial factory, but scaled down into a form factor that quietly sits on a desk in a government office.
It really fundamentally changes how you perceive the physical world around you. To bring this all together for you listening, the next time you're at the grocery store and you grab a bag of redolent medium roast coffee beans or a carton of organic milk, just take 1 second to look closely at that expiration date or that tiny QR code.
You just look at it.
You are not just looking at a stamp. You are looking at a highly engineered, chemically safe, instant drying marvel of thermodynamics. It is actively protecting you from counterfeits, it's keeping the factory line moving, and it is the invisible glue holding the entire global supply chain together.
Well said. And if we look at where this is heading, there is a small detail in the source material that hints at something truly revolutionary. HP is taking this precise fluid dynamics technology, the ability to use vapor bubbles, to drop microscopic amounts of liquid in exact programmable patterns, and they're applying it to bioprinters.
Wait, printing living biology using inkjet technology?
Yes. They are actively helping researchers print biological pharmaceutical samples.
Wow.
Which leaves us with a fascinating thought to ponder. If printing technology has evolved from simply leaving dark marks on paper to laying down complex chemical security layers that bond to plastic
Yeah.
and is now literally printing biological samples, how far are we from a future where the ink on our packaging is fully interactive?
Oh,
Could the ink of tomorrow be engineered to actively change color if the food inside the package starts to spoil? Or could the ink itself contain microscopic communicative properties, allowing it to actively talk to our smart devices to tell us exactly where, when, and how our product was born?
from a simple black barcode to a living, interactive digital nervous system, it really makes you wonder what the ink on your cereal box will be capable of doing 10 years from now. Until next time, keep diving deep.